Quantum computing, I mean, you hear that term thrown around everywhere, right? It's this technology that's supposed to change, well, everything. But let's be honest, the way we talk about it can sound a lot more like science fiction than actual science. So today, we're going to cut through all that hype. We're going to build a real solid understanding of what this revolutionary thing actually is, and just as importantly, what it isn't. You've definitely heard some version of this before, I'm sure of it. It's the standard, go-to pop science summary of how a quantum computer gets its incredible power. The idea is simple, right? A normal computer plods along, checking one answer, then the next. But a quantum machine? Whoa, it just looks at every single possibility all at once. Okay, let's really dig into that for a second, because that summary, while it sounds cool, it gives you some totally wrong ideas. I mean, think about it. If a quantum computer could truly check every answer at the same time, it would solve certain problems instantly. One step, boom, done, no matter how huge the problem was. But is that really what's happening? Well, the reality is a lot more subtle, and honestly, it's way more interesting. Take a problem like searching a giant database. The speedup is huge for sure, but it's not instant. So to find one item in a list of a million, your laptop might have to check all million entries in the worst case. A quantum computer? It gets it done in about 1,000 steps, the square root. Now, that is an incredible leap, don't get me wrong, but it's not infinite. It's not magic. And that tells us that the real power is coming from something much, much cleverer than just trying everything at once. So, to really get a handle on this, the first thing we have to do is completely reframe how we think about them. We have to stop thinking of quantum computers as just souped-up versions of our laptops. They are not an upgrade. They're a completely new species of machine, operating on rules that are just fundamentally different from anything we're used to. And this is probably the best analogy I've ever heard. A classical computer, that's like a car. We can always build faster and faster cars, but they're always going to be stuck on the roads we've already built. A quantum computer isn't a faster car. It's a boat. It's designed to leave the roads behind and navigate entirely new oceans of problems. Problems a car could never, ever get to, no matter how fast it's going. Okay, so if it's a boat, what's powering it? What's the engine? Well, it runs on the incredibly weird but wonderful rules of quantum mechanics. To get it, we really just need to look at three key ideas: superposition, entanglement, and interference. First up, we've got superposition. You know how a normal computer bit is just a switch? It's either a 0 or a 1. Simple. A quantum bit, or a qubit, can be a 0, a 1, or it can be a blend of both at the exact same time. The classic example is a spinning coin. While it's in the air spinning, it's not heads and it's not tails, right? It's in this kind of weird, fuzzy state of both possibilities at once. That ability to hold more information is step one. Next, things get even stranger with entanglement. This is a property so bizarre that Albert Einstein himself called it spooky action at a distance. When you entangle two qubits, they become mysteriously linked. If you measure one, you instantly know the state of the other, even if it's on the other side of the galaxy. They're no longer two separate things. They act as one single coordinated system. And as you add more entangled qubits, the computational space just explodes exponentially. But here's the thing. Superposition and entanglement are just setting the stage. The real magic, the secret sauce that makes the whole thing work, is interference. See, qubits also act like waves. And just like waves on a pond, they can add up and get bigger, or they can cancel each other out. A quantum algorithm is really just a beautifully choreographed process to make the waves for all the wrong answers cancel each other out to nothing, while the waves for the right answer all add up and reinforce each other. So, a quantum algorithm isn't like trying every key on a giant keychain. It's so much more elegant than that. It's more like holding the whole keychain and shaking it in a very specific, clever way so that all the wrong keys just fall away, and you're left holding the single one that works. It's this delicate dance of probabilities, all guided by interference to make the correct answer shine through a massive sea of possibilities. All right, so we've got our quantum boat. We have a sense of the weird physics that's making it go. So where are we going to sail? What are these new oceans we can finally explore? What are the problems that were basically impossible before? The applications really fall into three massive categories that could just reshape entire industries. We're talking about simulating the natural world with perfect fidelity, completely upending cybersecurity as we know it, and solving impossibly complex optimization problems that are crucial for things like logistics and AI. The legendary physicist Richard Feynman actually came up with the whole idea of a quantum computer for exactly this reason. Because the world, at the level of molecules and atoms, is quantum mechanical. Our best supercomputers today can only get a rough approximation, but a quantum computer speaks nature's native language. This could let us design brand new drugs from the ground up, create revolutionary materials for things like ultra-efficient batteries. I mean, we could understand chemistry in a way we've only dreamed of. Now, this is the application that has governments and security agencies in a flat-out global race. The encryption that protects almost everything we do online, your bank account, your messages, national secrets, it's all based on a math problem that would take the best supercomputer on Earth today literally billions of years to crack. A powerful enough quantum computer, it could potentially do it in a few hours. That would make our entire digital world vulnerable overnight. And then you have these monster optimization problems. Imagine trying to figure out the absolute best delivery route for thousands of trucks all at once, or finding the perfect investment portfolio out of millions of stocks. The number of possible combinations is just astronomical. It's beyond what any classical computer could ever search through. But quantum computers are uniquely built to navigate these huge complex landscapes, to find that one optimal solution. This could supercharge everything from logistics and finance to how we train the next generation of AI. Okay, this all sounds absolutely incredible, right? So if this technology is so powerful, why don't we have quantum laptops on our desks? Well, it turns out that actually building and running one of these things is one of the most difficult engineering challenges humanity has ever faced. For starters, those delicate quantum states we talked about, they are unbelievably fragile. The slightest vibration, the tiniest change in temperature from the outside world can just, poof, destroy the whole calculation. So to protect them, these processors have to be kept inside these huge, elaborate refrigerators at temperatures colder than the vacuum of deep space, just a tiny fraction of a degree above absolute zero. And that really brings us to the three monumental tasks that researchers are racing to solve right now. The first is what's called decoherence. That's just the fancy word for qubits losing their quantum magic because of noise from the environment. Then there's error correction. How in the world do you fix tiny errors in the middle of a quantum calculation without looking at it, and by looking at it, breaking the whole thing? And finally, there's scaling. We have to go from the hundreds of qubits we have today to the millions of stable, error-corrected qubits we'll need for those world-changing applications. And to put that scaling challenge into perspective, just look at this chart. Today's most advanced quantum processors are hovering around 400 or so qubits. But to break that encryption we were talking about, the estimates say we'll need well over 1 million high-quality stable qubits. So yeah, we are truly in the very, very early days. Think of it like the vacuum tube era of classical computers. So where does all this leave us? Well, quantum computing is not going to replace your laptop for checking email. It's a highly specialized tool for tackling a certain class of impossible problems. And even with all these massive challenges, it still represents a fundamental shift in science. It's a long-term bet on our ability to harness the deepest, weirdest laws of physics to see and shape our world in ways we never thought possible. And I just want to leave you with this thought from the researcher Scott Aronson. He imagines a future where these strange, abstract quantum algorithms aren't just things in a textbook, but are the actual tools that might one day determine the fate of the world. And it's just a powerful reminder that we are at the very, very beginning of a new journey into this computational ocean. We're just setting sail, and we have absolutely no idea what amazing new worlds we're going to find out there.